Welcome back to another explainer. Today we're diving into episode 6.3, TCSSBR, which stands for Trip Circuit Supervision. We're tackling what's basically the ultimate hidden vulnerability in power system protection. We're talking about the unassuming copper wire that literally guards everything else. We spend so much time securing the logic and the mechanics of our networks, right? Well, today, we're zooming in on the physical link that holds the whole shebang together.
Imagine this scenario for a second. Let's say every single protection function we've covered so far is working flawlessly. Your differential protection is spot on, your thermal and overcurrent elements are perfectly tuned, a fault happens, the relay instantly and correctly detects it, and it fires off that critical trip command to the breaker. But what actually happens if the physical wire connecting the relay to the breaker is severed?
Nothing. Absolutely nothing. And honestly, that is a terrifying prospect. Without that physical path, the smartest, most advanced protection relay in the world is completely useless during a real fault. The breaker won't open, the fault isn't cleared, and it just burns indefinitely. All of that incredible digital logic we've built up stopped dead in its tracks by a simple broken wire.
Section 1, the invisible wiring vulnerability. Let's get right into it.
So this brings up a really crucial concept: the physical separation between our smart protection relay and the actual heavy-duty breaker hardware. People often just assume that if a relay's front panel looks healthy, if its internal self-diagnostics are flashing green, then the whole protection chain is secure. But look closely at the standard configuration. Notice that distinct external wiring path running out to the breaker trip coil? The relay's internal software is completely blind to the fact that this external copper wire might have degraded, or say a connection wiggled loose over time.
Section 2. Introducing Trip Circuit Supervision.
That terrifying gap in our armor is exactly why we need a dedicated function to watch the wire itself. Think about a smoke detector in your house. Waiting for a massive fire to break out just to see if the alarm actually works is, well, obviously a terrible idea, right? You need to know it's ready before the smoke appears. That's why smoke detectors have that tiny continuous green power on light. It doesn't wait for a disaster, it constantly proves its readiness. TCSSCBR is basically the continuous green light for your substation breaker.
So here's exactly what this function does. TCSSCBR provides continuous supervision of the trip coil and its associated wiring. It's looking for open circuits or loss of control voltage. And it does this by quietly running this tiny, totally harmless test signal, we're talking about 1.5 milliamps, through the trip circuit at all times. It's just a proactive, constant physical ping. If that 1.5 milliamp current ever stops flowing, the relay knows instantly, hey, the path is broken.
Section 3. How continuous monitoring works.
Now here is where the engineering gets super clever. A circuit breaker isn't just a static device, right? It opens, it closes, it physically shifts the circuit's topology. So how on earth does the relay adapt to keep that continuous test signal flowing? Well, when the breaker is closed, the supervision current flows right through the trip coil itself, proving the primary path is intact. But when the breaker is open, that main path might be physically interrupted by auxiliary contacts. So the TCSSCBR function seamlessly shifts to supervise the circuit using an alternate parallel path. It makes sure the test signal is literally never broken.
This setup creates absolutely zero blind spots, and covering both the open and closed states is an absolute must. Imagine for a second if a supervision scheme only monitored the wire when the breaker was closed. The very moment you open the breaker for routine switching, boom, you've created a massive blind spot. If a wire happens to break while the breaker is open, you'd have absolutely no idea until you close it again and then, tragically try to trip it during a fault. Continuous dual-state monitoring completely eliminates that risk.
Section 4. Why periodic testing fails.
At this point, you might be thinking, hold on, don't we do scheduled maintenance? Don't we test these breakers periodically? We do, for sure. But the reality of the physical world is, well, it's unpredictable. Between those scheduled functional tests, a lot can go wrong out there in a substation environment. Wire insulation degrades from temperature fluctuations. Physical vibrations from nearby heavy equipment can slowly shake terminal connections loose. Or it could be something as mundane as a blown fuse or a trip control voltage supply breaker instantly killing power to the trip coil. None of those things care that you had a totally successful maintenance test 3 weeks ago.
Let's do a quick interactive timeline scenario. I want you to really picture this in your head. Say a critical breaker has been sitting closed and idle, perfectly normal for 3 months. Unbeknownst to anyone, the control wire developed a break 2 months ago because of a loose connection. In a system without continuous supervision, when does the operator actually discover this failure?
The answer is pretty devastating.
In an unsupervised system, you're going to find out when the next scheduled test rolls around or, way worse, when a real fault occurs and the breaker just straight up fails to clear it, leading to a massive outage or catastrophic equipment damage. Now contrast that with a system running TCSBR. The very instant that wire broke 2 months ago, that tiny 1.5 milliamp test signal dropped out and an alarm was triggered within seconds.
And that leads us to a completely non-negotiable operational takeaway. Rule of thumb. Any trip circuit supervision alarm must be treated as an urgent, immediate threat. It does not mean something might break soon. It means the breaker is effectively crippled right now. If a genuine trip command comes in while that alarm is active, the breaker will not operate. The grid is essentially unprotected in that zone. You investigate it immediately. Section 5. The complete protection chain. Let's pull back and look at the big picture for a second, anchoring this all back to our actual hardware. By adding trip circuit supervision, we are slotting in the final critical piece of the local substation protection puzzle we've been building over these past few episodes. Take a look at the RET615 protection and control relay. This device is acting as the central brain synthesizing all these complex converging functions. It's reading the high voltages, crunching the differential algorithms, monitoring the mechanical wear and tear, and, as we now know, proactively pinging the external copper wiring, all from this single hub.
And this brings our local protection chain to a true state of completion. Step 1. The relay logic flawlessly detects the fault. Step 2. The SSCBR function has already verified the breaker's mechanical health is solid. Step 3. The TCSSCBR function guarantees the electrical pathway is perfectly ready to deliver the message. We have successfully secured every single link, from the digital brain inside the relay all the way down to the physical copper wire attached to the breaker.
So we've got an incredibly robust, self-diagnosing, highly secure local bay. But here is the next massive challenge. With this local chain secured, how do these independent, highly intelligent devices actually talk to each other across an entire facility? How does a relay in Bay 1 instantly coordinate with a relay in Bay 4? Well, that is where the magic of the IEC 61850 communication standard comes into play. And that is exactly what we're going to unravel in the next explainer. You absolutely won't want to miss it. See you then.